We're now going to look at the best technique for solving differential equations. It's called the separation of variables. This is what you're going to use in introductory calculus, and this is what we always use at a first glance at differential equations to see if it works. So let's start with an actual example. Okay, number one, I'm going to solve the differential equation dy dx equals, and then we've got x times the square root of y. Okay, so our goal here is to solve this differential equation. We want to, keep in mind what it is, right? It is a slope field, if you like, and we're trying to find out the equation of the curve that goes through it, okay? It's an equation, and it's looking at what's the rate of change, and there it's expressed, but we need to find out what is the y. When you take dy dx, we'll actually give you that. So the separation of variables is that you separate the y's and the x's. That's simple. So the idea is you can think of dy dx as two separate differentials. You basically cross multiply, move the dx up with the x, but then this y variable you're going to bring down with the dy. And so when we do that, we end up with dy over root y equals x dx. Okay? Now the reason why we do that is because now the way you solve differential equations is you can now integrate both sides. That is the key. You can't integrate both sides up here. I mean, you could write integrals down, but it doesn't make sense. Now when you write integrals to both sides, it totally makes sense because these are integrals that we've had and done, right? We've got y to the negative 1/2. Cool, so what do? We add 2 halves, right? And we get y to the 1/2 divided by 1/2, that's times 2. So we get 2 square root of y, and then this is going to be clearly x squared over 2. Okay? And so we're just about done. There is a constant, and if you like, okay, there's a plus c1 here and a plus c2 there, and then you can subtract them and get, a c3. But what you do in differential equations is there's just a constant, and so you just add it. So just add it at the end, plus c. Now, this is considered a satisfactory solution to this differential equation. It's not required to solve it in terms of y. Okay, I mean, you certainly could, right? We could say what y is. If we did this, okay, we divide by 2, and then we would get, and so this is not necessary. Okay, let me just put it in here, just so you can see. So you would end up with like square root of y. Just have with that marker. Let's try another one. So you would end up with the square root of y, and then that equals x squared over 4. Now, you would also have the c over 2, but like c over 2 and c, it doesn't really matter. It's kind of the same thing. So I would actually just call this one c. If we like, we could call this one something else, like c prime. Because remember, c is just a constant, and so you don't need it like c over 2. It's just a constant. Take c over 2 as your constant. And then, of course, you could square both sides. So both are correct, but I'm just showing you this. It's totally not necessary because in differential equations, you often end up with complicated expressions where it doesn't make sense to solve for y. So we know that we can solve for y, and this would be considered okay. Okay, let us look at another example, okay, of a differential equation. How about this one? Number 2. Color here, and we'll say y prime equals x e to the y. Okay? So for 2, y prime equals x e to the y. Okay, so separable equations. Send the y's and the x's on different sides. Now in this one, okay, you might be a little thrown because this is y prime, this is dy dx. Well, these are the same thing, right? This is just an x and a y on the right side. So you would rewrite it actually as dy dx equals x e y, and then it's just like what we did before, right? And the x is like the same thing. You would get dy over y, sorry, dy over e to the y, and then this is just x dx again, and then you just integrate both sides. Right? The whole point of separable equations, okay, or separation of variables, is that when you separate them, okay, and you get all y's to one side and all x's to one side, because you have a dy and a dx, or whatever it is, dt, t's and dt's, then you can integrate both sides. That's the point, okay? It's a method. And so e to the y is e to the negative y, so it would be negative e to the negative y, right, because it is actually negative, or negative 1 over e to the y equals x squared over 2 plus c. And so that is, we're done. Sure, you could take the natural log of both sides, but that is the solution to this differential equation. Okay? So hopefully you're getting the idea of the technique here. Let's look at another example. Okay, so number 3. And let's go with dz dt equals, oh, sorry. Not going to do it equal this time. Okay, I'm going to do something a little different. We're going to do plus e to the z plus 2t equals 0. Okay, so how do we separate these variables? You know, sometimes you need to do a little work to sort of set up the separation of variables. So the dz dt is great. That's what we want, right? We started with that both times. So that's good. Now to start a separation of variables, so I'm going to copy this. It's good to send things to, like the other stuff, really to the other side. Okay, when it's on the same side and there's a plus, that's not good. You want sort of like the times thing happening. So this is going to be equal to the negative of e to the z plus 2t. And hopefully you are aware of another way to write that. Because as it stands, it's I don't know, it's still not entirely clear. But if we rewrite it as dz dt equals negative e to the z e to the 2t, now we're in business. Because now we have separated on one side the z from the t. When I say separated, I think of it in terms of multiplication. These are two separate terms. That's what we have here, two separate terms. That's what we have here, two separate terms. And so we have two separate terms multiplied that allows you to use the separation of variables technique. Okay? So that's what we do. Now we just send them together through multiplication, and we get the dz over, say, negative e to the z equals dt e to the 2t, and now we can definitely integrate both sides. Okay, so we integrate both sides here. These are just e's. We, you know, it's e, like in this one, we get e to the negative z, the negative makes it a positive, so it's e to the negative z equals, and this is just e to the 2t, but it's times 1/2 by the chain rule. I say by the chain rule because if you use the chain rule to get that, right, take the derivative, you'd have it times 2 and they would cancel. And then once again, we just add on the plus c at the end. Okay, let us do now a slightly different type. Okay, and the different type that we're going to do is the following. Okay, so we are number 4. Check out the markers here. Okay, so number 4. We've got du dt equals 2t plus secant squared t all over u, say 2u, and then you have an initial condition here. And the initial condition is that, so this is the first part, and then we have a second part, and it says that u of 0 okay, equals -4. Okay, so this is an initial condition, and the idea of an initial condition is you solve just like we've been doing, but at the very end, you're gonna plug in for 0, and that's going to deliver the C, right? Remember we had the slope fields and there are all these different curves? Well, this is one specific curve, right, at the point 0, -4. So first step, just solve the differential equation. Separation of variables. So we just cross multiply. So we got 2u du equals, and then it's 2t plus secant squared t dt. Okay, that's what you want, right? Now we can integrate both sides. Do our integrals. We get u squared equals t squared. And then sometimes you have to think of things like, what's the derivative that gives you the secant squared? Well, that would be tangent, right? Derivative tangent is secant squared. So it's tangent of t. And then we need our plus c. Okay, so far so good. The point here is that u of 0 is -4. Okay, what does that mean? Okay, what's what here? Okay, what it means is the variable is t. So when t is 0, okay, this is like our t, u is actually -4. Okay, that's what it's telling you. Okay, let's say that again. When you write it like this, what this means is the variable, the other variable, not the u, the t, is 0. And so what's left? The u is -4. And the reason why I'm emphasizing this is because often you'd have y equals. And so then you set equal to -4, but this is more like a substitution. Okay, so we're substituting in -4 for u, and we're substituting in 0 for t. And we get that 16 is equal to c. And then what we need to do now is rewrite the differential equation, which is right here. And we rewrite it as u squared equals t squared plus tangent of t plus 16. And so now we don't have a general differential equation, we have a very specific differential equation. Okay, so here are some examples using separation of variables along with an initial condition problem. Those are standard in differential equations, so you want to get practice with those and get used to them. The only other thing I will add is occasionally, let me just put up one more. Occasionally you will see problems that, it's not really clear how to separate them. And so let me just do one example of those. We won't solve it because we don't have the room, but let's just do the separation. So here's the setup. It's still not working. The setup would be dy dx. Okay, so that part is clear. Then we have minus 2xy equals x. So how do we, I guess this is like we're starting number 5. How do we, it's tricky because, I find it's tricky for some students. You want the dy dx by itself, okay? Send everything to the other side. Okay, so this gives us dy dx equals 2xy plus x, right? Because you're adding the 2xy. Okay, so this is better, but it's problematic because the x and the y are stuck together. So how do you unstick them? All of these problems, one term times another. That's the key. So how do we get in one of these terms times another? You factor it. Okay? And so this becomes dy dx equals, pull out the x, and you're left with 2y plus 1. Okay, and then now you can clearly separate them, and you would end up with the last one, dy over 2i plus 1, and that equals x dx. And then clearly you can then take the integral of both sides, you get a natural log, you get an XDX, and you are home free. X squared over tuitions.